LC-MS is short for liquid chromatography and mass spectrometry. The LC-MS instrument is essentially a combination of high-performance liquid chromatography, which is a technique for separating compounds with different properties, and mass spectrometry, which is a technique for the detection and identification of compounds. LC-MS is a highly useful tool because it can allow scientists to separate components of a mixture of compounds while simultaneously determining information about the structure, mass, and identity of the separated compounds. Mass spectrometry as a technique has existed for a century. Its roots began in 1899 when J.J. Thomson and his lab assistant E. Everett developed an apparatus that measured the mass-to-charge ratio of electrons. Based on this work, Thomson and his protege, Francis Aston, were able to build the first ever mass spectrometer, which measured the mass-to-charge ratio of atoms. Over time, scientists in multiple fields became aware of the use of mass spectrometry for separating different isotopes of elements. For some time, however, scientists didn't really understand what went on inside the mass spectrometer. It was a black box, a mystery no one would solve. That changed due ultimately to the work of three scientists, Frederick Lafferty, Klaus Biermann, and Carl Djerassi. The work done by these scientists revealed the fragmentation mechanisms of different organic molecules, and thus greater insight into the functioning of the mass spectrometer was gained. In the 1980s, another big mass spectrometry breakthrough came with the ionization techniques ESI and MALDI. These made it possible to analyze larger molecules such as proteins, which could not be analyzed using previous techniques. Liquid chromatography also has its origins from 100 years ago. In the 1900s, Mikhail Tsvet developed a technique of using a column packed with stationary particles and a liquid eluent to separate different components of leaf pigments extracted from plants. He dubbed his technique chromatography. Liquid chromatography techniques continued to develop in the following decades, and in the 1970s, the innovation of high-pressure liquid chromatography, or HPLC, made this analytical technique even more powerful. With smaller packing particles and higher pump pressures, the performance of liquid chromatography was improved, and the technique name was changed to high-performance liquid chromatography, though still called HPLC. In 1968, the first ever attempt to combine LC and MS was done by Victor Talros, and several decades of technological improvements have made the LC-MS instrument a very powerful tool indeed. Analysis begins with the injection of a sample into the LC-MS. Once injected, the sample will be carried by the liquid mobile phase and enter the column. The column contains a separatory resin referred to as the stationary phase, which interacts with an analyte in such a way as to cause it to remain in the column longer. This is called retention. There are several types of columns that are commercially available, with different types of stationary phases depending on the type of separation that is desired. The ideal stationary phase is one that has properties that allow it to bind to your analyte well enough to cause significant retention in the column. For example, one of the most common types of columns is a reversed phase chromatography column with a nonpolar C18 stationary phase. If a polar mobile phase is used, then this column will retain species that are relatively more nonpolar for a relatively longer time, and species which are relatively polar will elute out faster. As the analyte solution passes through the column, the individual components are separated and elute from the column at different times based on how much they are retained by the stationary phase. The analytes are detected by a UV detector as they exit the column. Once the compounds in a sample have been separated, they move onwards into the mass spectrometer. First, the analyte compounds are ionized by an ionization source. Mass spectrometry measures not mass, but mass-to-charge ratio, or M/Z. Therefore, analytes need to be ionized for them to be detectable by the mass spectrometer. There are several types of ionization sources, with electrospray ionization being one of the most commonly used for LC-MS. Once the analytes are ionized, they pass into the mass analyzer portion of the instrument. There are multiple techniques for this portion of the analysis, but the cheapest method is with a quadrupolar electric field. For this type of instrument, ions pass through an electric field generated by 4 cylindrical electrodes. In this setup, only certain M/Z ratios are stable enough to pass through the quadrupole. Thus, by varying the electric field, you can separate your analytes based on their M/Z ratios. Once the ions pass through the mass analyzer, they reach the ion detector, which then generates a graph of relative abundance versus M/Z ratio. When all analysis is finished, you will obtain a chromatogram from the LC portion of the instrument, coupled with the mass spectra from your MS detector.